Hi, welcome back to a new episode program with C. In this episode, we'll be looking at functions in C programming language. First, we'll be looking at programming functions and its type in general. Then we will be discussing specific type of functions that is called user-defined functions. Then we'll be looking at the syntax of recursion in C programming language. Finally, the storage class. Of course, we'll be discussing number of lab examples to illustrate those outlines. Now, before we start actually discussing the first outline, I would like to revisit a technical tip which we have discussed in a previous episode. That is the question, how does computer understand the code? We have seen some answers for this question, however, the answer was quite a bit generic. Now, since we have proceeded so far in a number of episodes, it is the time to touch some real technical aspect of the same answer. So essentially, let's actually revisit the concept of any machine. There are two important pillars, besides, of course, some other pillars as well. However, the most two important one is called the CPU and the memory. CPU represents the central processing unit, with the execution of any instruction the machine doing, and we want the machine to do, it's done on this particular part. And then you have the memory part. In the memory, it's a kind of a storage place where we actually place our instructions, and then the CPU access to those available addresses one at a time and execute the instructions. Now, when we look at the memory hierarchy, there are so many ways to actually discuss the topic of memory from different perspectives about the size, about the speed, the budget of the memory, etc. Now, this pyramid you could see on the screen represent a structure or hierarchy of a memory, starting from the very fast and most expensive type of memory to the least one. Let's just start first of all with the first type of memory, which is called the register, which is actually close too much to the CPU. Of the way it is engineered, it actually provides an instant access to the information it contains. That's why one of the fastest type of memory you could think of in the hierarchy or the structure of memory. However, of course, because its location on the CPU and the CPU is limited in its size itself, the size of the register, it doesn't offer you much of a size that you can deal with. That's why the use of registers, although you have the capacity to do that and place some variable directly in the register or store them there, you have to be quite a bit careful. Now, the second type of memory is called the cache type of memory. Now, cache is a kind of a special memory. It's smaller and faster than normal main memory, which we are going to discuss in a while. And it's housed close to the CPU, as you could see in that structure in the screen. It maintains a copy of part of the main memory, and it allows a quicker access to some information. The fact is that as far as the logic of program goes, this cache does not exist physically, but rather logically. We always request information from the main memory, which is the RAM, and the cache makes it so easy actually to access directly to the CPU. You could think of a cache actually as a kind of priority type of instruction need to be executed. But the most important part to be understood is the actual physical type of RAM, which is called the random access memory. Now, there are so many different versions that could be of the type of the SDRAM, the DDRM. RAM generally needs power to maintain its state. It means whatever information we store in it, it needs power. Once we shut down the computer, whatever information was stored, it will be actually gone then. That's why we need sometimes data to maintain its state regardless of the power. This is where the secondary type of memory. For example, you got the hard drive, CD drives, flash drives. These are actually can store information long term, regardless of the power state. But they are way slower than, of course, the RAM itself. And actually, the CPU does not have a direct access to these type of memories. That's why whatever is stored in this kind of memory or secondary memory will be first loaded on the main memory or the physical memory, and later on the CPU will be talking to this main memory. In our actually focus, whenever we speak about memory, we are talking about this particular part in the graph. That is the physical memory. Now, from this slide onward, every kind of a tip that we're going to talk about is actually talking about this particular piece inside that pyramid. That is the physical memory. Now let's move on that particular piece of the physical memory and try to have a better graphical view on it. Basically, as we have seen before, if we write any piece of code, I have to pass it to a compiler. And we know now the job of the compiler is to actually convert that code into a language the machine can understand of value of zeros and ones. Now, how does actually the machine itself understand such ones and zeros is not the focus of this series of episodes. This can be focus of the second edition from the Big Bang of Data Science, which we expect to be released in the near future. But as far as this number of episodes concerned, is to actually understand the perceptual idea up to that part where the machine later is going to actually understand the zeros and one. There are some of blocks you have to understand. The first block is called actually the text block, where the machine code or the machine instructions is stored out there. On top of that, you will have another part, or the section part 2, that store every kind of global and static data there. Now, what kind of global and static we're going to be learning in a while, but this is where the global and the static data is stored. Now, the next part, and one of the most important part, is called the stack part, where the parameters are stored. The actual code, the functions, the variables, and everything we talk about once we write a piece of code is stored in that particular part inside the memory. The last part is called the heap, or the dynamic variables, where, as the name implying, every dynamic access to some variables that we can actually, during the cycle of the application, place and remove will be stored out there. So the difference basically between this stack and heap, stack, it happens once we launch the application and we can't change its size. However, the heap, we can use it anytime during the life cycle of the application. Now, these information are quite a bit important to be understood, at least from a graphical perspective. Later, once you write your application, you should imagine that so your application become more efficient. Let's now take practical example. We have an application executing certain task. First thing we need to understand that once the compiler actually compile and I launch the application, the first part inside the memory is the part you see in the screen called the stack frame will be created and will be allocated with number of bytes. Now the stack frame is located and you can't, during the life of your application, exceed that. If you exceed, throw an error and jump your computer. Now, the actual application of C programming language, it goes line by line. Beside calling the include headers, which we're going to discuss in a while, the first line actually has been called is declaration of a global variable. Now, this is a variable or identifier of type integer, which actually take 4 bytes in the memory. This is where the global and the static data is taking place in this second part. In this graph, you could see, since it was not explicitly assigned with any value, 0 will be default value assigned to this global value. So this is the exact things happen to the first line. Now, there are 2 more lines. You could see integer function 1 and void of function 2. Why are they there? Previous labs, when we were actually creating different function, I said it's preparation for the future. And the time now to understand, I was writing the function on the top and then main was always at the bottom. And why was that happening? Because of the conceptual idea of stack. Always in the stack frame, one particular function cannot be removed during the life cycle of application. That is the main function. And on top of the main function, every other function or whatsoever function is going to take place, it will comes and goes as the application requires. So the first thing I place on that stack is going to be the main function. That's why the first 2 lines, we are actually telling the compiler, hey, listen, there are 2 functions will be used later on inside the stack, and they will come on top of the main function and be aware of them. The first one called function 1, which take an argument of type integer and actually return integer. The second one, it takes an argument of type integer and return nothing. It's called function 2. So now the compiler is aware of 2 functions will take place on top of the main function as the execution goes on. Now the main function starts its own execution. Now, the first line in the main function is to call a print function. Now, printf, it's another function which is called actually from the header file called the standard libraries, which we include in the top of the code, as you can see up there. It just print a line called illustration on the memory. And once this print function does its own job, it will be removed from the stack and free up whatever size has been located in the stack. And the control come back again to the main function. So you could see this a transmission between the main frame when it was paused and give control to the printf. And once the printf does its own job, it removed itself from the stack, freed up the place, and give back control to the main. Now the main function in control again, and the second line is to printf again another function. So again, it's called another printf function. Now the printf function is taking control, and it actually print another line called a global variable state1. However, in this case, it need this printf function to have access to a variable, and this variable happens to be global. That's why it goes and look at the global variable value of 0 and take that value and print it out to the screen. That's why the second line you could see global variable state1 is equal to 0. And once it's done and printed out, it will actually be removed from the stack and give back control to the main. Now the main function is in control. Now the third line in this code, it actually called function1, and it passed an argument with an integer number of 10. Now function1 is taking control. That's why you could see now the line goes to function1 in the stack, and function1 basically receives that integer and it does some own work. First thing what it does, it have initiated its own variable, which called a result function1. It's a variable of type integer. That means there are 4 bytes inside that particular space in the stack will be located, and it does some kind of math on it by adding another integer. And then basically what it does, it return whatsoever value to the main function and actually release itself from the stack and get back. And that's why the main function now has a control back. But this time the main function, it realized whatever returned, in this case a value, it will assign that to the global variable. So again, the global value will be manipulated by the main function this time. That's why the global value now, the value will be updated by 15 and actually passing to the next line of printing the global variable. It has the value of 15 this time. After that, this is where function now 2 is taking place or taking control. It has this value of 10 and it does some work. As far as this type of function, void, it means it does not return anything, but it does something in its body. Basically, it just updates the global variable. You see the global variable accessible by every other function, not only the main function. And that's why when it's done and it releases itself, the function 2, and say, I am done, it just updated the global variable to be of value 25, and then it removes itself from the stack and free its space. Now the main control, it has its own control. Finally, it called the printf function again, which is going to print actually whatever the value in the global variable. That was the last line, global variable state3 25. Now I hope this perceptual understanding is clear to you, how actually the sequence happens between the code and what's going on inside the memory, how the stack is actually managing, and where's the location of the main variable, the globals, the heap later we'll be looking at in some other part as we proceed in this episode. Now, one last step further from very, very deep technical aspect. We are too close now to the physical memory. Now, inside the code blocks here, this simple code you see on the screen, which actually done nothing special. First, of course, I'm calling the standard library headers, and then I am in the main function defining this variable called a and assigning to value of integer. I'm giving a certain value. I'm calling the printf, and I'm printing a returning 0. So you could see nothing special. However, the most important part to be understood here, once I go here and I click the button of build and run, and you could see the screen here, which actually it does exactly as expected by printing the value of a is equal 972. What is going on here and how the code blocks actually does the work. If I take you to the actual main folder where the code block have stored this project, first, this is the main C where our code has been written. Now, there are 3 different files here, which one of them actually represent the project itself. Another 2 files, actually, code blocks has its own structure, which is actually an XML file. In fact, if I would have to open one of these, like the machine code.layout, and try to use just the notebook and open, you will see that is an XML format, which actually code blocks taking care. If you are using any other IDE, you will have a different structure. But the most important part, I want to share with you these 2 folders. One of them called the bin folder and the other called the object. Bin is actually indicating the binary format. Now, if we open this bin folder, we will see this machine code.exe. This is the execution part, which we said the compiler have converted whatever code into the language of zeros and one. But there's also another file inside the object folder called actually the main.o, an O indicating an object. Now, if you try or attempt to open this using the notebook, you shouldn't be surprised to see this kind of unreadable characters and files, because this is a kind of a binary. That's why here I would like to use a tool called the object dump tool, which actually have some argument can be taken. In this case, let's take an argument called the simply, and then I just have to mention whatever file I would like to deassemble. Now, what you see in the screen here is the actual assembly code, which is one step before the actual machine code of zeros and one. This is the most primitive type of a programming language. It's been used so many years ago by so many people actually to create an applications. Now, every line you see here is actually how we arrange the information or the instructions. We located different bytes in the memory. So basically, these lines you see here is the way we are talking to the physical memory. Now, you don't have actually to read this. You don't have to learn about it at all, but it's not harmful to understand what's going on within this assembly code. Let's get back to our main focus. The code is in here, which we have seen that I'm defining inside the main function an integer, locating a number for it, calling the print function, and just printing it on the screen. What's going on here, if you look at the 32-bit x86 assembly language programming, you could see this is a structure which actually represents somehow whatever we were talking about, the physical memory. There are 2 important suffixes that you have to understand this graph if you would like, of course, to navigate your knowledge. The base pointer, another thing called the stack pointer, responsible on this particular stack location where we were talking about. When the application starts, we said it locate number of bytes, and the stack now will hold those number of bytes throughout the life cycle of the application, have to be within the particular stack of bytes. Now, basically, if you look at the assembly code in here, first we'll be looking at the main function. These first 2 lines, it tells me actually to locate or to push the base to the pointer, where I am actually speaking about this particular part, which is 3 and 4. Stretching this 4 part to take as much as I want depends on the application and how much memory we need to locate in their physical memory. But the interesting part actually to see at calling this 61 main function, here's where the actual main functions start. Now, the next line I would like to share with you is this line called the 0x3cc, comma, minus 0x4, and the base. What this line means and how to read this line, basically it says, the main function here say, I need an integer and I'm calling it A. Integer type, we know, allocate 4 bytes in the physical memory. Actually, 0x4, it means 4 bytes. And it's in a hexadecimal. If you would convert this hexadecimal, you could see actually the actual value in decimal number is 4. And 4 actually is the 4 bytes that we spoke about of type integer. That's why in this line, actually what I'm saying, I want to locate 4 bytes inside the stack. And then in the next line, A, or whatever is they identify as a variable, is equal 972. I'm saying, well, in that particular address, or these 4 bytes, I would like to assign this value. Now, this 0x3cc in hexadecimal, you shouldn't be surprised to see the value of 972 decimal, which is exactly the value that we assign to A. So this line basically it says exactly that. So I want this 4 byte and locate this value inside these 4 byte. That's it. And it makes some arrangement and load them and everything. But the most important part here is call the printf function, which is you could see in that line. So if you call the printf function, now we go up to the printf function, which is taking place now on top of the stack, as we have seen before, and goes through some lines of arrangement, etc., location. But the most important line I want you actually to look at, and you shouldn't be surprised, is this location 0x4, which we have located here, these 4 byte. It says the printf function. I want you to move there and print whatever in that particular location. Since we have actually done with this piece of technical information, how does actually computer understand the code? It is time now to get back to our main focus, first outline, that is programming functions in C programming language. There are 2 types of functions in C programming language. The first type called standard type of functions, and the second one called user-defined kind of functions. Now let's first of all look at the standard library functions. Now these are built-in functions in C programming language. And these functions are defined in some type called a header file. Actually, we have used these kind of header files so many times when we were calling in the first line, include specific header files, and then we proceed on using some of their functions throughout the applications. There are so many different header files. In fact, you can write your own header files that you can utilize later on for your application, or other people also can utilize those functions. Here I am sharing with you a number of those header files can be really handy while you are executing certain tasks. For example, let's just start with the first one. Type of header files called the assert header files. In fact, this assert header files, it works as a kind of debugger, so to speak. So sometimes when you write piece of code, and if your code really gets so long with so many lines, it could be so hard to find the mistake. Now, for example, you could see here in the screen, I have a function called other function that actually accepts 2 arguments, x and y, and do some operation and return another variable called z. For example, imagine this other function to be an addition. So if I would have to pass 3 and 4, I would expect, for example, return value of 7. However, if the application return, for example, 1, now the compiler will not throw an error. But 1 is actually a wrong answer. It means I messed up the operator while creating the other function. Use of this assert headers, it gives me an ability actually to debug the other function before I actually rely on its value. In this case, I could call the assert function and I pass the other function with its 2 arguments, and I am asking, is the return value is going to be z? In this case, for example, I would say other function with 3 and 4, is the return value 7? If it isn't, the assert function will actually quit and print an error. There is another header file called the C-type header file that offer you a lot of built-in function, for example, to deal with characters. If you would like to check if a character in the lower or in the upper case is printable or not. This snapshot of some of the function, but so many other functions also include in this header file. Another one called the math function, as the name is implying. There are so many functions, exponential functions, the log function, etc. Instead of reinventing the wheel, you could utilize those functions. And there's another one called the setJump function. Actually, it's a very powerful header file. Let me show you a general idea. First of all, the use of setJump function, of course, after you call the header, is to define a global variable, a data type defined by the setJump function. And for example, in this case, I'm defining an identifier called buff. And then I go to the main function. Now, in the main function, the first line says, I want you to check a condition. Now, what the condition says, it calls a function called setJump, expect an argument. And I'm passing that a global argument buff. Now, since it's a global and I didn't explicitly set it with any value, we know now the value is going to be 0. We will fail this condition, so we're going to go to the else. The else, the first thing, we're going to print DAHMAN'S Phi 4 with a new line, and then I'm calling function C. Look carefully what happened now. I go up to function C. The first line I will print welcome to DAHMAN'S Phi, and then I'm calling the function called long jump. And in long jump, basically I am assigning to this global variable buff a value of 1. Once this line took a place, what happened, whatever after that is not going to be executed. and it go back to the main function. Now you might think, okay, that's what usually happen, but this case, it doesn't take me back to the main function from where I stopped, but it take me to the beginning of the main function. So basically it goes again to the top of the main function, checking the condition, which is now equal to 1. And then it goes and print DAHMAN'S Phi 3. So in this line of code, if you follow the logic, you should expect first to have DAHMAN'S Phi 4, and then welcome to DAHMAN'S Phi, and then DAHMAN'S Phi 3. But DAHMAN'S Phi 2, it will never be printed. And that's exactly the result as expected you see in the screen. Now, another header file called the standard arg.header file. Powerful type of header file. It has a lot of actually application. One of them, I would say, it allow indefinite number of arguments. Now, as we know, functions take number of arguments sometimes. So I could define a function to add 2 numbers. Now, when I say add 2 numbers, if you try to pass to this function more than 2 or less than 2, the compiler will throw an error. But imagine in some cases you would like to add, but you don't know how many numbers. Sometimes could be 3 numbers, sometimes 4 numbers. It means you have to write for every number of argument different functions. But how about one function can receive any number of argument, depends on whatever you want. And that's exactly the actual implementation of standard argument header. It gives you an ability actually where you could define one function and can receive as many arguments as you like, depends on the structure. We're going to be looking at an example later on. You got the standard input header, a contain number of functions such as the printf, the scanf, and so many others. You got the standard library function actually. Also, it offers a number of utilities, so to speak. For example, to generate random numbers, or maybe to exit an application, or to convert a character of any ASCII number into a float or an integer, etc. And then you have a string header libraries, which actually contain number also of useful functions, such as checking, for example, the length of a string. All right, let's now check the second type of functions in C programming language, and that is a user-defined kind of functions. We have worked on user-defined functions. We have defined our own function. Then the main function is going actually to call that particular function along the line. So if I pass some lines and then I reach to function name, main function will stop there and give control to that function. And whatever this function does, as it finishes, it goes back to where it has stopped, to the next line after its previous call. There are some important terminology you need to be familiar with. As we have said before, the structure of the stack, the main function always need to be at the top of the code because it is in the bottom of the stack. And we need to inform the compiler there are some other functions out down there. They will be later on called. That's why we have this first line we call the function prototype. Basically just say to the compiler, listen, there's a function called add numbers, take 2 arguments, and return a type of integer. It will be called later. The next important terminology called the function call, which we have seen before. In this case, for example, add 2 numbers and take 2 arguments, and whatever value returned from there will be assigned to this variable called sum. The next terminology called the function definitions, which we should be familiar with now, defining a function with whatever argument takes. Finally, the return statements. So these are terminologies just be familiar with once we talk about user-defined functions. But the important part now, I would like to introduce you to 4 different user type functions. The first type takes no argument and return no value. See this function called check prime numbers. Basically, I call it in the main function, and the check prime number of type void, it means return nothing, and actually take no arguments. We can see just open bracket. And it does everything, call the user to enter an integer, it does the check in out and print and everything. The second type take no argument but actually return a value. Look at this function called actually the get integer function. Basically in the main function, I want actually to assign a value to a variable called n of type integer. Now instead of doing the work on my own, I decided to create a function called get integer, which basically take no argument at all, but the get integer is going to prompt the user to enter a value and to return whatever the user have actually entered to the screen. The third type take an argument, but it return no value. So in this case, for example, check prime and display. Basically, the main function, it does the prompt to the user, it takes the value, and it passes whatever the user give to check prime and display. Now the check prime and display receive that variable, does the job of printing on the screen, but actually return nothing. The last type, it's actually, as you could expect, take an argument and return a value. For example, here the check prime number, the main function, it prompt the user, it take the value, and it pass it to the check prime. Now the check prime take that argument and does some work or check out on it, and it returns something to the main function. Now which one type is the best depends on the task and the structure and the design you are working. Now let's talk about an important syntax in C programming language called recursion. Now as the name implies, it's a concept where a function calls itself. Let me start with this task, say to sum of a natural number using recursion. For example, if I would have to provide a number and I expect to sum that number with its previous numbers up to 0. Now to do this task, I could apply any of the flow control we've learned about with loop or whatsoever, but the concept of recursion can be powerful here. For example, look at this piece of code here. Essentially, we are actually prompting the user to enter a value, and after that, we call the sum number function. So here, the main function will be left and create on the stack the sum function. The first thing the sum function does is to check a condition. It says, well, this argument you passed to me, and by the way, the sum function of the fourth type, take argument and return a value. So once again, it take that number passed by the user, check if it isn't 0, what it does, it actually go to this return line, go and call itself. Keep doing that until this condition n is not equal to 0 fail, and then I go to the else. In this case, I will return whatever. Now when it return, it doesn't go to the main, it go to where it has stopped. Now I want you to imagine from stack perspective what's going on the physical RAM. Let's focus on this particular line. So imagine from the main function, I am saying the user enter number 3. Now this number 3 will pass the main function. 3 is not equal to 0. Of course, it will go 3 plus the sum of 2. Now the sum of 2, again, the sum function is calling itself. So it go again, 2 is not equal to 0. It passed 2 plus the sum of 1. Once again, the sum called itself. 1 is not equal to 0. So it go 1 plus 1, of course, 0. Now 0 go again. Is 0 not equal to 0? It's not true. It means it will go to return 0. Now this will go backward. I want you to see now every layer here placed in the stack on top of each other, on top of the sum of 3. That's why you have to imagine you are occupying part on the physical memory. And now you should start to imagine why recursion sometimes can be encouraged if you misuse the recursion. You could really exploit all the available space until you reach to the stage where you overflow fault error message. That's why now what happened, since I met the condition of return 0, now return 0 will go back to the last stop where the sum of 0, which is going to be 0. Now 1 plus 0 is 1, will return to the previous one. 2 plus 1 is 3, return to be 3, and finally return 3 plus 3 be 6. And that's why the final outcome of this application will be sum of 6, which is actually true. Now, the last things I would like to talk about before we go to the lab is the storage class. There are 4 different concepts of storage class when it comes to C programming language. You should be familiar with all of them by now, but let's try to illustrate that through this code you see on the screen. First of all, let's look at this global variable. And we know now the location of the global variable in the memory, as we have said before. Now, this global variable, unlike before, we assign a specific value of 5 to it. Now I am in my main function. My main function, basically, it call or it initiate a local variable called A. Now this A will be stored in the stack inside the main location, where the main function actually has its own number of bytes. Then I'm calling another variable called R of type integer. However, you could see the keyword register. And why register here is taking place? Because what I am saying, I want you to store this variable on the register. And we have seen register type of memory is at the upper of the pyramid. This is a very rare case. If you are not actually aware of what you are doing, you are placing this variable to be quick access by the CPU. This case can be useful if your application requires certain variable to be accessed so frequent. Instead of storing that on the stack, you can actually locate it in the register memory. I hope now you can imagine. Still R is only local variable to main, but its location is going to be stored on the register memory. Next, we are actually just incrementing this global variable called n by value of 1. Then we are calling the display function. Now we are leaving the main function, going to the display function. Now the display function is creating another variable called a. You have now to recognize this A and the previous A has nothing to do with each other. One of them belong to the main, and this is locally defined belong to the display function, and it's assigned to a value of 5. Again, I'm creating another local variable called B of type integer, and I'm assigning a value of it. But I'm using a keyword called static, and now you should understand where this B is going to be stored. Basically is not on the stack. It will be on that location where you could see in the graph in that block 2, where the global and the static data will be stored, available to the display, but its location of store will be on the global and the static part. We will see why that can be important sometimes. Next, I am again accessing that global variable. I am incrementing its value by 1. Here's the first printf function. Go to the global variable and print whatever value. Now the value is going to be 7, although I initiated and by 5. Because in the main I incremented by 1 becomes 6, and now I incremented again, it becomes 7. That's why the value now is 7. Then again I am printing a new value called im variable a in the display function, and my value of 5, which is we just initiated out there. And again I'm printing a new line. It calls im static variable b. In this round, my value is 10, which is b. Again, a static variable belong to the display function and it's printed with the current value b. Look here what I have done. Actually, I went to this b local variable of type integer, which is a static storage class, and I'm adding a value to it. That's it. Now display function will be removed from the stack and the control come back to the main function. The main function basically is going to print this line called im variable a in the main function, and my value is 3, which we have initiated earlier. And of course, I'm just printing another line called this round is over. Now I'm calling the display function one more time. Here is a new life cycle of this display function. Will take on top of the stack, and again the first line of to create a variable called a, assign a 5 to it. Now watch carefully what happened. This stack integer initiation of b will not happen again because it has been initiated once and stored in the global and static data. That's why the keyword static is in there, and it will not be revisited again. But we go to the global variable, we increment by 1, and again we are printing the value. Of course, the previous or the last value of the global was 7. Now increment by 1 is going to be 8, and then again I am printing the variable a in the display function with value 5, which has just been initiated. But the interesting part to see this static variable b, and the current value now is 15 because the previous one was 10, and then we added 5 to it before we left in the previous round. That's why now we are printing 15, and of course again I'm going to add one more time to this 15 of the 5. If I would have to call display again, I will say it. That's it, and that will be the end of this application. I hope now the entire mechanism, how the actual code and the structure and what are functions in C programming language is quite clear to you. Let's go ahead now and actually execute number of tasks in this lab. The first task is to look at debug with this header file we call the assert header files. Now I'm in the code blocks file, and this is my project. And essentially, the first thing to do, it's not like a strategy to create, it's just a test actually to include this particular header file that we're talking about. So if I say include, and I want you to call the assert header files. Now it's been called directly because it is located in the folder that we have seen just before. Number of header files are there that we can include them. Now, first of all, you could, of course, you create your function and then you can make the prototype here, or you write your own function directly here as you wish. It doesn't really matter. So let's actually create a function. Let's call it, for example, add numbers function, which take 2 arguments, as we have done actually the example. Let's say add 2 numbers together and just return the value. So basically, if we define z variable, and basically z's will be equal to x plus y, and then we're going to return z. Now in the main function here, what we want to do actually, as you expect, of course, is to call the add function. So let's first of all call this kind of variable called result, and we say, well, the result will be equal to whatever add number, and then let's pass, for example, 4 and 5. And this actually, let's print this. However, let me say, as I am writing this function, the add function, somehow I have missed, and instead of putting that operator, I put that operator. Now for the run the application, 4 plus 5 equals 0. There is no error has been thrown by the compiler because the operation is legitimate. I did not divide by 0. Nothing is wrong with that. I'm just returning 4 divided by 5 is 0. That's it. When you have really long code, the use of a assert function can be really a lifesaver. Let me show you here an example. What I'm going to do before we actually print, I would like to just call the assert. I'd like to add 2 numbers just to check this function is working well or not. So I'm going to pass this 4 and 5. All right, and I'm asking, is it equal to 9? Because this is what I know it should be the right answer. Let's now run this and see what is going to happen. We've got a new thing. See, assertion failed. Now add number 4 and 5 equal to 9 is wrong, and it tells you at line 15. Now what is line 15? Is this guy here where I have actually checked the code. It say there is a problem, and there's nothing executed afterward. That's why it stopped me at line 15, and then I get back to my line 15 here, and I see, okay, now the condition is not right. It means my add function has a problem. So if I get back to my add function, imagine if this is thousands of lines, I get back to my add function, then I discover my operator was wrong. Now if I run this one more time, the application would just go as it's been expected. So this particular line just to debug whether our function is working well or not. This is one of the application with assert, which could you see really powerful and useful. Let's now check a new task. And this task say, well, I would like to work on function that accept varied number of arguments. Now in this case, what I'd like to do, I would like to work with this standard args headers, which we have discussed before. It gives me an ability that if I would have a function and I don't know how many arguments or the number of arguments can change depends on. Sometimes I would like to print 2 arguments, sometimes 6 arguments. I don't know, depends on certain condition. In this case, if I would have to call include here, standard arg header file, there are important function, or a number of them actually, 3 or 4, that you have actually to recognize already before. First one is the data type, which called the VA list, and the second is called the VA start function, and the next one called the VA arc, and then after that you have to be familiar with something called the VA end. So let's actually create an integer function. Let's say a print how many integers I'm going to print. Sometimes I'm going to print 2 integers, sometimes I'm going to print 5 integers. I'm not clear about how many integers I would like to print. That's why here in the main function, what I could do, I would like to call print actually, and then I pass something like that. This is my whole numbers here. And again, I want in some other condition to print again other list of numbers. So you could see the challenge now. If I would have to call print, I don't know now, shall I make print with only 5 or 6 arguments, or maybe I make print with 2 arguments? Unless I say, well, I have to make a 1 print or with 6 arguments, another print with 2 arguments. And this is not the right thing to do. And this is the powerful of the use of standard arguments headers. Let's see how that actually works. First of all, define here a type of integer, say the number of arguments, and take 3 dots. You should now recognize why these 3 dots. It says, well, whatever number you pass to me here, for example, say number of arguments, I'm going to pass to you this time 5 numbers. So these 3 dots will represent those 5 numbers. If number of arguments 2, you expect these 3 will represent only 2 arguments. This is the structure. First thing you have to understand. Now, the next thing you need to do is actually to define something called VA list type. We said here, this is the first thing you need to know. It's a data type. Now, let's call this one for simplicity args, for example. The next thing I want to do is to call this function called start. It takes 2 important arguments. You see V and L is actually written for me there. The first thing, it takes the data type of VA list, which is going to be args. In this case, we have just defined. And the next thing, it takes the L argument you would like to pass, which is going to be actually the number of arguments that we spoke about just now. Let's define an integer called I and assign it to a number of 0. And I say, well, as long as this I is less than number of args that we are intended to do, I'm going to add 1 to it. Now, the important part to observe after we go inside the loop is to call this an integer type. Let's call it the value. And let's actually call now the varg. Now, the varg, basically, it takes 2 arguments, again, V and L. First, I will take the args, which now is going to be actually transforming those args one at a time, and is going to be of type integer. That's exactly what's going to happen. Now, we should anticipate the next line, what's going to be, just to print. Finally, we must call the end function. Watch carefully what is going on. I am saying, well, I want you to call print function. Print function, of course, since it's constructed with the standard argument headers, expect first of all the first number is passed to be the number of arguments. Now I'm saying I'm going to pass to you 3 arguments or 3 arguments only. So anything after this number will be what is going to be printed. So I'm going to print 4, 5, and 6. I don't need the 7. And I'm just looping here. Number of arguments anyway is 3. And I'm assigning from 0, 1, and 2 as long as this I is less than 3. So if we would have to print this, you should be able to see the values expected, that is 4, 5, and 6. These are only 3 values. Let's check the last task to create a function to calculate the power. Now in this example, I would like to use the recursion or the concept of recursion that we have spoke about earlier on. Maybe we can prompt the user to enter the number and the power. So we can say power function. All right, it can be exponential actually. It's the same concept. And it's called base, okay? And then maybe we could call the other one as A. It's going to be the power anyway. And basically what we want, if as long as this A is not going to be equal to 0, power of 0 is going to be 1 anyway. So we can say as long as that, I want you to return the following. See, 1 line only. I want you to return the base, whatever it is, multiplied by. Here is the interesting part. We're going to call a function itself. Just only function itself is going to be the base and pass to it actually the A minus, the power that we pass minus 1. That's it. Put the else. I'm going to return 1. Why? Because it will be power of 0. Anyway, it will be 1. Now in the main function, as you could expect, of course, we're going to basically make an integer with base and A, maybe with the result as well. Let's print here the prompt the user the base number. Of course, we're going to scan that. And same thing for the power. And here's the result. And maybe we could print that out. Basically, let's enter base of 3, power of 4. The answer is right. It's 3 power of 4 is just 81. That was all for this episode. Look forward to see you on the next one. Till then, stay good. Cheers.